I didn't have to talk or teach in, so that was nice. Here we go. One consequence of the early and dramatic successes that scientists enjoyed when using calculus to explain natural phenomena was that there suddenly seemed to be no limits, so to speak, on how infinite processes might be exploited. There was still considerable mystery about infinite sums and division by infinitely small quantities. In the years after Newton and Leibniz, remember they were the ones that just started all the calculus, but even mathematicians normally insistent on rigorous proofs were inclined to throw caution to the wind, while things were working. Interesting. The result was a century of unprecedented progress in understanding the physical universe, and proofs eventually followed. One infinite process that had puzzled mathematicians for centuries was the summing of infinite series. Sometimes an infinite series of terms added up to a number, as in, now here's cool, here's a visual of why 1/2 plus 1/4 plus 1/8 plus 1/16 eventually converges to 1. You guys see what's going on over here? You have one whole cut in half, and then you have the half cut into a fourth, and then you have the fourth cut into an eighth, and then a 16th, and a 32nd. It's a geometric proof for why this infinite series has to be 1. You're getting closer and closer and closer to the 1 unit. However, sometimes the infinite sum was infinite, as in, who's this guy? 1 over n, p series, p equals 1, also known as the simple harmonic series, equals infinity. Now, let's see what follows. Although this is far from obvious, right? We're still struggling with that one. And with improper integrals ln, it kind of starts to make sense. And sometimes the infinite sum was difficult to pin down, and some of you have gotten stuck on this one. 1 minus 1 plus 1 minus 1 plus 1. Is it 0? Is it 1? Is it neither? Nonetheless, mathematicians like Gauss and Euler successfully used infinite series to derive previously inaccessible results. Infinite series to derive previously inaccessible results. Laplace used infinite series to prove the stability of the what? Infinite series to prove the stability of the solar system? Although people still worry about it today when they feel that too many planets. Okay, there's more to that, obviously. But infinite series to prove the stability of the solar. It was years later that careful analysts like Cauchy developed the theoretical foundation for series computation, sending many mathematicians, including Laplace, back to their desks to verify their results. So basically, they were doing all this stuff, being like, it's working, it's working, it's working, and then they're like, oh, crud, maybe we made something or proves or said something wrong, so they all went going back. But here we go, right here, this last paragraph. Our approach, our book's approach, in this chapter will be to discover the calculus of infinite series as the pioneers of calculus did. Proceeding intuitively, accepting what works, rejecting what does not. Towards the end of the chapter, we will return to the crucial question of convergence and take a careful look at it. What does that mean? This book doesn't start with, hey, here's all the convergence and divergence tests of all the different types of sequences and series, let's go. Our book says, I don't know, there's these things called infinite series. Let's figure them out. So, our section 10.1 was geometric. Let's talk about them. Introduction to geometric. And so as it was introducing geometric, it was talking about even things like the associative property of addition, talking about how, way over here, introducing sigma notation for the first time, introducing a series will converge if the sum of, or the partial sums converge. So these are big ideas that we talked about in the other books, chapter 9, right? Identifying a divergent series that covered the question of 1 minus 1 plus 1, what is the answer to that? And it's like, well, if someone starts grouping it like this, well, yeah, it looks like 0 plus 0 plus 0, but the problem is that requires infinite pairings, which you cannot get. So the associative property of addition breaks down. Instead, you have to think of partial sums, 1, 0, 1, 0. Oh, of course it diverges. It doesn't know what it's doing. But then it says, but this guy converges, boom, 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 geometric series. 0.33333 is a geo. So it introduces geo series basically with repeating decimals, which is why that came back. Does that make sense? And so you guys saw repeating decimals in homework when you were... when the book moved on, it started to zoom out and say, okay, repeating decimals, that's great and all, but let's also talk about just any common ratio, not just repeating decimals, not just that application. So then it started talking about nth terms and forming nth terms for geoseries, finding the common ratio, talking about, at the very beginning of geoseries, they said, hey, this thing, r between 1 and -1, is called an interval of convergence. And then they start to introduce the infinite sum of a convergent geometric series. Then they started saying, oh, hey, you know what? Since we're talking about geoseries, without having talked about any other series, any other convergence or divergence, they say, by the way, what if we make Rx? And then they go in talking about basically how this polynomial, which they're like, well, it's not just any polynomial. They had already broken this idea of an infinite series of numbers, how it's not merely a sum. They're like, this addition of powers is not a mere polynomial. It has much more implications that are going to follow. P.S. Let's introduce the idea of a power series. So, long story short, our book is covering it in a very experimental way, a very exploratory way. And so there are going to be things like, oh, P.S., sorry. Right here at the very bottom is where we ended yesterday. How they were like, we've only been doing geo. Can we make any other conclusions about any other power series of anyone who's not geo? And it's like, yeah, we can derive geo and derive the power series and get a new power series for a non-geo function. Or we can integrate, or we can integrate a geo series and then get a power series from integrating the original geo's power series of a non-geo series. So at the very, very end of section 10.1, they're like, hey, guess what? We can express any geo series as a function, or any function as any rational function. Oh, I can't even say that, can I? Any function that fits the form a sub 1 over 1 minus r as a power series. Or we can expand that at the very end. We expand that by deriving or integrating any power series formed by geoseries and their corresponding functions. And then I want you guys to start off class before we grade section 10.1. Go into the back of your homework spirals and do the following. This is an introduction to Taylor polynomials and approximation. And if you read the very top line, what does it say? So we just ended geoseries and seeing that geoseries can express functions, certain types of functions. Deriving, integrating, expand it a little bit more, and now you're being introduced to the idea of, hey, polynomials, aka maybe these power series things, can be used to also express things like sine and e to the x and ln of x. Ready, set, equation of a tangent line? What? Isn't that like, I don't know, first semester CalcAB stuff? Ready, set, go. It's in the back of your homework spiral. It's just the beginning. Just linearization, local linear approximation, tangent line approximation, basic stuff. Although when we were doing a slope field FRQ this morning with calculus AB, it wasn't so basic to them. I don't know. They haven't seen tangent lines in a while. It was so sad. It was like, use the tangent line, and they were like, huh? It's hard enough just to get them to say the equation of a line. And just a few of you are like, what am I doing right now? Y minus y1 equals m times x minus x1. Y minus f of a equals f prime of a times x minus a. Yeah? If you want to, CalcBC style, you can name the y L. L of x, move everything to one side, and then plug in your L of 0.2. Maybe some year I'll teach series the way our book does. I don't know. 0.2, yeah. You don't need to. Because you're not plugging into cosine of 0.2. Remember? Right? How we doing, team? Right, to find the y1, we just plug into sine, and then to find the f prime or the m, we plug into cosine, because that's the derivative, true? So then we end up with L, the local linear approximation of 0.2. Sine of 0 is just 0, yeah. Cosine of 0 is just 1, and then we have 0.2 minus 0 is 0.2. So what do I think that sine of 0.2 is approximately? 0.2. Someone throw it in your calculator just because I'm curious as to how close we got. But as you do that, graphically, what does that mean? See, I'm going by 2 pi's. So there's my pi. There's my pi. There's my pi over 2. Pi over 2 is approximately, hey, it's March. It's coming. Okay, coming back though. Besides pi day coming, pi is 3.14196 divided by 2 is approximately 1.5-ish. So 1.5-ish, 0.2-ish, well, pi over 4, that'd be 0.75-ish. 0.2 is really, really close, right? The tangent line skimming the sine curve should be pretty close. Only hits at 1 point, but it should be pretty close. The actual answer, Aryan, what'd you get? 0.198. Ah, 0.198. Now, did we know that that was going to be a perfect approximation? No, because we knew it was going to be approximate, and we knew that 0.2 is a little ways away from 0, and we know that the line hits in 1 point. No, it looks like it perfectly skims. Ah, it's because you need to zoom, 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 zoom in to see it diverge? Oh, dear. 0.198, is that what you said? Okay, is approximately 0.2. We knew that it was going to be a little bit off, right? Okay. But how can we make it more on? I don't want to say it quite yet. We'll wait. I want you to go one more time. Remember yesterday, for those of you guys that were here, I gave you a peek behind the curtain. And I said, you know, sine of x can actually have, or actually does have, a polynomial that approximates him as well. Yeah. I want you guys to go ahead and, if you still have it from yesterday, I don't know if we went all the way out to x to the 7th over 7 factorial, but here's what they're saying. We already know what y1 of 0.2 is because you guys just found it. But can you go ahead and plug in 0.2 polynomial approximation really quick? Plug in 0.2 to that polynomial approximation really quick.
Like for x?
Uh-huh. The same way that we just plugged it into the tangent line, plug it into x minus x cubed over 3 factorial. Wait, if you still have this in your grapher, can't you just do y whatever you have, parentheses, 0.2 or 0.2, parentheses? But careful, I don't think we went to 7.
No, we didn't. I just added
Yeah. So for those of you guys that still have it in your y, I think it would have been y1, 2, y3, y4.
Well, y4 without, but that's missing the x squared over 7 factorial.
Got it. Now, if worse comes to worse and you weren't here, or you didn't put it in, or you already erased it out of your graphing calculator, just type it in. You can do 0.2 minus 0.2 cubed over 3 factorial plus 0.2 to the 5th over 5 factorial. Let's see how close this is. It's not the infinite sum. We're still cutting it off. It's a partial sum. It's a polynomial that I said yes. All right, I'm going to need a few more decimals from you, I think. Okay, so it was 0.19. Give me some more.
866. Oh, so I guess it should be right back.
Oh, I got. Oh yeah, I got that.
What'd you get?
7
First time. Like, it's exactly the same?
Yeah.
What?
I got 0.198661396.
Oh, 661?
Yeah, 661.
So, no. That's so much closer than the last one, right? You see it? How much closer was this than that? A lot closer. Why? Because if you graph this polynomial, a 7th degree, oh, I just took them all away. Lo siento. What's the difference between the line skimming? This would have been just y equals x. This would have been y equals x minus x cubed over 3 factorial. This would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. And this is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Question, who does a better approximation? That guy or that guy? All the way. Did you guys check your decimals? Did it go off at that last decimal place? 9 and 1?
Mine's the same.
Oh, it's the exact same?
I got the exact same. I don't know.
Ooh. Maybe that's something that we have to ask ourselves. Is it the exact same, or is it just getting closer and closer? Do their decimals change? Well, according to our graphing calculators, we can't tell. So it was 669?
I got 6.
Okay. So all that to say, in section 10.2, we're going to say we can make a polynomial, a power polynomial, out of any function using... What? Isn't this local linearization right here? F of a plus f prime of a times x minus a. We just never knew there was a whole other world out there that would let us get closer and closer and closer for more and more and more terms. Section 10.2 is where we're going today. If you guys want to grab a quick picture of it, you can be taking the notes as we grade homework. But we are going back to homework because you guys, have you seen the evens yet? I don't think so. So color pens out, section 10.1. Let's go ahead and grade those evens. Yeah, we did odd questions, but not the evens at all, right? So take a picture of the notes if you guys want to be taking them. Some of you aren't ready to grade. Totally fine. Take a picture, be using it. Yeah, that's perfect. That's perfect. I just needed a comment to remind me of what I said. For those of you gone yesterday, if you didn't watch the video or the video cut out before I said this, we were talking about how weird homework felt. Because I'm in the whole like power series, let's introduce it. And they're like, series in general, let's just talk about geo. Anyway, so very different feel. So then that's why we did some extra practice yesterday. And I was like, okay, if you didn't finish or if you didn't post it, just post me a quick comment about like, you said you'd give us grace, and then I will. So here we are. I have the book open, but I also have the evens open, section 10.1. So did you guys literally have them asking about convergence and divergence of geoseries? Yeah, because our book was like, hey, geoseries, let's learn it. So it was as easy as r is 5/4 greater than 1, divergent. Number 44, you were making, I don't know, in my head it's easier to write out, I don't even write decimals, ugh, I write fractions. But either way, at the end of the day, 6/100ths was your initial term and 1/10 was your common ratio. Ew, I don't like decimals. Anyway, 1/15th ends up happening if you use fractions or if you use decimals. I won't totally judge you using decimals, except who would do that in their head? I don't know. Do some of your heads like this better than fractions? Right? Like, ugh. Yeah. No, same. Okay. What were you doing?
She expects us to do that in our head with her calculator.
Just go team go.
Yes. And she would get it exactly right, and we're like, okay.
No, she's a stud.
Calculator dependent. We're like, no. Put like the cube root of the student decimal, and then you guys can just make it a fraction and like reason it out.
But you have to remember when she did math, like high school and college, like they had the slide rule and everything was, yeah.
I don't know how she does it.
Yeah. No, it's crazy.
She would like make fun of us.
Number 56. There you go. Interval of convergence is just between 1 and -1 because x cubed was your common ratio. And cube rooting 1 and -1 stays the same. Did that make sense? Sure. That's helpful. 68 is C and 70 is E, and I think that's it. So I'm ready for questions because I just heard a sure, and that's never a good sign. Any evens or odds remaining from yesterday? 41. And then Kathy?
Just the thing yesterday, I checked on it, and I don't know, I'm still confused because it was...
Can you give me a problem just to refresh my memory as to what we're talking about? Sorry, Kathy.
Yes,
Problem number 21.
know if that's legal. And then for the equation thing, I got 1 over 1 minus 2x. Should I do
No, I'm hearing what you're doing. I'm trying to figure out where your question lies. Because to be honest, my brain is fuzzy, and so I know you started asking me yesterday. But yeah, give me 1 second to get 41. Hold on, Kathy. We'll talk about yours first. James, did you have one too?
Maybe
50.
power series and then also interval convergence.
Okay.
I got the interval right, but I don't know that.
Okay. Oh, we could do that to make it a little bit faster. I have 21, 41, and then you said which one, James? 56. Does anybody want 41 if Maggie takes 56?
I can do 41 instead of 56.
Does anybody want 56 instead of 41? Okay, then I'll just take them. Thank you, though, Maggie. Let's start here, and then if we have any other ones, we can go for it. So, Kathy, remind me of my directions for number 21. Okay, so I would have rewritten this, and I think this is what you were saying, 2x to the n. Is that what you were thinking? And it always helps in my brain, especially if it's going to be geometrics, to start plugging in. So the first term would be 1, and that's pretty important. But then every term after that is just times 2x, times 2x, times 2x, right? So far, so good? So then the sum of an infinite series, where'd you go from there, Kathy? So plugging into the formula, what'd you do? Yeah, because it was the first term.
And then I got 1 minus 2x.
You said 1 over 1 minus r.
And I think when I look back, it was 2x minus 1 or something like that. And I didn't really understand.
Oh, I guess they could have pulled out a -1. I don't know why they would have. Did anybody else check the back of the book and it looked funny? It didn't just match up with a1 over 1 minus r. What is this? 10 point something something?
I got that too, the Kathy.
Oh, kiddo, I think you were just looking at the wrong one. Number 23 has 2 over x minus 1. But 21 is 1 over 1 minus 2x. So you were totally right. You just got thrown off a little bit. And then when you do your IOC, remember we always start with our common ratio between 1 and -1, since it's a geoseries. So then x is going to be in between, divide everything by 2, -1/2 and 1/2. But no, you're good. That was right.
I guess like
Oh, yeah. It was a different one. That was the weird one.
it was 27, and it was just finding
Okay.
the derivative and then going from there.
And so what was the series for 27? Was that going back to 21?
Yeah, it was using the series for 21.
Okay, and you were supposed to take the derivative of the function and then take the derivative of the power series, which was 1 plus 2x plus 4x squared plus 8x. That's what we're doing, right? Looking back at 21. Is that good? So then taking the derivative of this guy can make him to the -1, so I could bring down the -1, so that's going to be 1 minus 2x squared times -2. So it was a negative times a negative. Positive? Does that look good, guys? For your derivative of your function. And then I would have derivative of 1 is 0. That's awkward. Lo siento. 2 plus 8x plus 24x squared plus. Now, in my mind, it's really hard to look at this unless I think about what's really going on. So that's why it's nice, and I think the AP has you has you focus on doing nth terms, because up here, if you had figured out this is really just 2x to the n. N started at 0 on this one, right? Then I could put as my nth term, I could be like, I'm smart. I'm going to bring down the, let's see, n times 2 to the n, x to the n minus 1. And I don't even have to think about my nth term because I could just take the derivative. So I thought about 2 to the n is my coefficient, x to the n, bring down the n minus 1. So that makes it a little bit easier as far as my coefficient. What was weird, Kathy, in what they did? Got it. They didn't like how this was written. This is right, but see what else they could do. What if they rewrite this? I don't know why they did this, but couldn't you pull a negative out of both? Ugh, it doesn't even look nice doing it. Well, yeah. Because it is squared, see? And you pull the negative out of both. And it's weird. It totally is. I don't know why they're doing it, but they aren't wrong. Because technically, this is going to be the exact same as this, because a negative times a negative is a positive. So the idea is when you have a squared or a fourth or a sixth, you can flip the signs, and it's exactly the same.
Oh, so can you do that for anything?
Even powers, yes. Odd powers, no. Does that answer a lot of other questions, maybe?
Yes, thank you
Cool.
so much.
All right.
If you left it the first way, just to throw 1 minus x squared.
It's technically right. Just think about match how it can be tricky. This would be the exact same as that. Great. No, FRQ would have been totally fine. Riley, number 41. I don't know. My brain works so much better just writing it out. So 234 over 10 hundredths thousandths. And then it'd be 234 over millions. And then I see in my head, hey, r is equal to, I need 3 zeros every time. Is that good? And so then I can use this guy as my a sub 1. Got him. Because now I can say a sub 1 all over 1 minus r. Pretty quick, 999 over 1,000, and then the thousands reduced, so 234 over 99. You guys yesterday said 9 goes in? 9 goes in 26 times, and 9 goes in 111 times, and I think that's it. But that's what it is asking for. It's just asking for a fraction whenever it puts the wording of rational functions or something, right? Find a rational function, just find a ratio, find a fraction. Last but not least, 56. James, are we trying to do a power series? Okay. Remember, we're trying to compare this as much as is possible to a1 over 1 minus r. Nice thing is, this one's gorgeous. Times x cubed. And remember, when you're more powers, you're adding them. So then I end up with 3, which is multiplied by everybody, and x to the 0, 1, 2. I guess it depends on where we're starting. We could do 3n starting at 0, or we could do 3n minus 1 starting at 1. Either way. Is that cool? Yeah. Sorry, guys. I answered the 3 questions, or 4, but that's okay. Were there any other ones, evens or odds, you wanted to see?
Question. For 56, so they're just asking to find the answer? That was the instruction?
Oh, that's a great question. I have no idea. James, what were the directions on 56?
Find a geopower series to represent
Oh, interval of convergence.
an interval.
My bad. My bad. Interval of convergence. Oh, actually, that ended up being pretty nice in this case because the interval of convergence, my r is x cubed in between -1 and 1, and all I have to do is cube root, which is still -1 to 1. Yeah. Then we're good? Cool. All right, guys, section 10.2. Let's go look at these Taylor polynomials because we were like, okay, as of this point, we can do power series for geoseries and derivatives and integrals of geoseries. That's it. So how do we expand that? Well, we expand that to what some of you guys were taking notes on while we were doing homework questions, or what the rest of you guys will be taking notes on now. Yeah. Let me check really quickly as you guys are getting it down whether I want it to be 2 or 1. Maclaren's, if you guys notice it, are the exact same thing as Taylor's, just what's the one difference? Or what's the one special case? Centered at 0. Yeah. Centered around, centered at 0. So basically they're found the exact same way. One centered at 0 and the other one centered at A. We had a bit of a difficulty with some of those that we were trying to make centered at A yesterday. But the nice thing is today we're not necessarily having to make anything centered at A. At least not in the same way as taking a rational function and having to work backwards. That's not what I want. I want BC Endeavor cards. At some point, I updated the Endeavor cards for you guys. There you go. I don't think I've made it totally up to date. No, I did. I got all the way through the convergence and divergence. And we haven't had to add anything yet this chapter because Geo series, well, we have that power series one. So let's go see based on last year. Now, last year, I think the numbers are a little bit different than your guys's for one reason or another. But let me unfreeze the screen really quick so you can see what I'm seeing so that we know how to number these. Limit comparison test, alternating series test, absolute conditional, ratio root, Taylor polynomial. Okay, 2 different cards. But let's go find our numbers as far as where we're at. So we are at 24 and 25. Oh, it's the exact same. Go team. All right, 24 and 25. Taylor polynomials and Maclaurin polynomials. And then we are getting to some special ones that we're going to memorize that I kind of alluded to yesterday. So let me go ahead and steal all 3 of these. And I'll go ahead and paste them into your guys's. 24, 25, and 26. Don't link. Okay, so coming back to our notes. Thanks, guys, for letting me figure that out. This is Endeavor number 24. Endeavor number 25. So the crazy thing is every time you guys were doing local linear approximation, every time you were doing tangent line approximation, you were actually using a first order Taylor polynomial to approximate. I just didn't tell you that. First order, what? Well, you could use a first order Taylor polynomial or a second order Taylor polynomial or a third order. Ooh, what does the wording match up to? If this is a first order, and that's a second order, and that's a third order, and a fourth order, and a fifth order, if they're asking for a certain ordered Taylor polynomial or Maclaurin polynomial, it has to do with the same thing as the nth degree, the degree that x is being raised to. All right, we got it? Uh-oh. Just a few of you were amazing and were totally tuned into homework questions and you're catching up. Can you still see it if I go to the next page? I'll try to let you guys know what's on the next page. Because here's what they're asking, because the wording's going to be way too small for most of you to see. They want us to find the Maclaurin polynomial of degree n equals 5. All right, guys, let's go ahead and focus on n. I'm sorry, my brain gets so distracted when other people are talking. So here we go. Find the Maclaurin polynomial of degree n equals 5 for sine of x. I can't focus. Maybe it's because I'm sick. Here we go. We're in a new example, so no one's written this down yet. Find Maclaurin. That's our example. Find Maclaurin equals 5. So for those of you guys that can't see, we're going for a Maclaurin. We're going for a Maclaurin polynomial. That's important. Where n equals 5, f of x equals sine of x. Then we're going to use P5 of x to approximate sine of 0.1. Now they keep on going and start talking about error and all this sorts of stuff, but let's just go ahead and start here. So how do we form a Maclaurin? We start with a tangent line and we keep going, which might not make sense in your mind, but it will the more and more you get familiar with the formula. Because to get your p sub n, well, to get your p sub 5, you start with f of a. Well, if it's a Maclaurin, it's going to be f of 0. Plus f prime of, so a is 0, because x minus 0 needs to be your a. And I'm wondering how it all ties together. Just think a tangent line centered at 0, because that's the point, centered at 0. So start off with a tangent line, f of a, f of 0, plus f prime of a, f prime of 0, times x minus a, x minus 0. Well, that's just x. And keep going until you get to the fifth degree, or the nth degree, whatever it is they're asking for. So f. And of course, I can't write. Brain. Don't give up now. Double prime of 0, all over 2 factorial times x squared plus f triple prime of 0, all over 3 factorial times x cubed plus quadruple prime of 0, all over 4 factorial f. Do you guys remember? Some of you got confused by it last year. They can use numerals for the primes, but they can also use numbers, right? It was something silly on one of the mock APs. I remember you guys didn't like it. Uh-oh, Justin, you sound like me. Hang in there, bud. Issa's gone today. And then Sally's gone today. And Carrie's gone today. Huh?
Nothing.
Oh. So how are we going to find f prime, f double prime, f triple prime, f quadruple prime, etc.? It's sine. So couldn't we technically just be like, oh, okay, well, I mean, if you needed to, if it was a hard one, I guess we could write it off to the side. And sometimes if they give ones that aren't those special ones that some of you actually saw me from what we did today, there is a special one from sine. But why is it what it is? Well, because my f is sine, my f prime is cosine, my f double prime is negative sine, right? My f quadruple prime is negative cosine. My f to the 4 cosine. Hey, you're going to have to practice derivatives? Good team. You're welcome. But if it's a Maclaurin, what are we plugging into every single one? 0. So what sign is 0? So when I go to plug in that guy, just 0. When I go to plug in every other one is sine, right? So that's going to be 0, that's going to be 0, that's going to be 0. Hey, all the even degreed ones are going to be 0. So what's going to be left behind? Wait a minute, what's cosine of 0? So positive cosine is going to be a positive 1, so this is going to equal positive 1x. And then negative cosine is going to be negative 1, that's going to be. And then positive cosine is going to be positive 1, so x to the 5th. And the nice thing is we don't have to take more derivatives because don't we know where this would have kept going? There's a pattern. What's a nice way of memorizing this? What kind of symmetry does sine have? Even or odd? Which one? Help. Okay. Obviously, this isn't working well. Ready? What kind of polynomial is this centered at 0, 0? X squared, even. Just think x squared, even, symmetry. X cubed, odd symmetry. So sine is odd. Why am I saying that? Sine keeps the odds. Guess what cosine keeps? The evens, because it's going to be every other. So it's an easy way of remembering your Maclaurins for sine and for cosine. Wait a minute, we were supposed to use this thing, just like we use tangent lines. What were we supposed to use it for? To estimate. Now guys, didn't we just see a second ago that these make really, really good approximations? So can we go ahead and just move on? I could have you plug this in as well, but we just did it with 0.2, which is even closer than 0.1 to the 5th, all over 5 factorial. What this says is, finally, compare your to the actual value of sine. Is it in your interval? Interval? What interval? Find the error for your approximation and determine an interval in which sine of 0.1 could actually live. Have we talked about error of non-geometric series? Yes, as long as they are. What is this guy doing? Can I talk about his error? Yes. Okay, so what's his error going to be? Isn't my series positive, negative, positive, negative, positive, negative, and doesn't an alternating series say the error is going to be less than the absolute value of the next term? What would the next term have been? 0.1 to the 7th over 7 factorial. Why didn't I put a negative? Its absolute value. Well, wait, look at your sequence. Your alternating sequence is the evens. It's the next term. So your alternator, what's the next? The 7th. Does that make sense? Okay, because our alternator's right here. Our next term would be the 7th. And so if you throw that in, can anybody get that for me real quick? What's 0.1 to the 7 factorial? 5 factorial is 120 times 6 would be 720 times 7 would be 5,040, but with lots of decimal points?
I got 1.98 to the 10 times 10 to the negative 11.
Oh, 1.98, how'd that happen? 1.98 times 10 to the what? What did I do wrong? 5 factorial, 1 times 2 times 3 times 4 times 5 is 120. 120 times 6 is 720. 720 times 7 is 49 and 14, and carry the 1, 5,040. A 0.1 to the 7th? 0.1 times 0.1 times 0.1 times 0.1. Oh, divided by 5,040. That's what I wasn't doing in my head. Yeah, no, I'm not doing that in my head. What is this? 0.00011 times and then 198. How stinking close is our approximation? Close. Okay. What else do we have? So what if they were to ask us something totally different? And what if they were to say, find the find the Taylor polynomial? Aw, now what? Mostly the same thing. I'm going to have f of, but not 0 anymore, because I need x minus 1. If I need x minus 1, can we build this, guys, just based on tangent lines? If a is 1, then isn't that 1 and isn't that 1? So what's going to happen next? Isn't it going to be f double prime of 1 all over 2 factorial x minus 1 squared? And isn't it going to be, how long do I keep going for? Okay, so for right now, hold on, just because we're running short on time. You would keep going. But how am I going to get my derivatives for this one? Who's my guy? Oh, that's not a big deal, right? So if f is my ln, then what's f prime? What's f double prime? What's f triple prime? Do you see how you form these? Get out of here. Homework's due on Tuesday. Hey, guys, can you just take a second over the weekend to be like, do I care about